Figure 1 shows two parallel wires carrying 10 amps and 8 amps with currents going in opposite directions separated by 10 centimeters and Q, which is 10 centimeters below wire number 2. Calculate the resultant magnetic field at point Q. This right here is 10 centimeters. And so first thing you want to do is find the direction of magnetic fields. The magnetic fields are going to be going around the wire. So do the right hand rule. This is coming out of the page. The current is. And so we place our thumb along the direction of the current and wrap our fingers around the wire. And the way we wrap our fingers means that the magnetic field is going to be going that way. And specifically at this point Q, it is going to be going to the right, completely horizontal. So now we're going to do the same thing but for wire number 1. So this is going into the page, thumb going into the page, wrap your fingers. It is going to be going this direction. Magnetic field. Yep. And it might not look like it, but this, since it's 10 and 10, is actually a 45-degree angle. Or if you prefer radians, we'll call it pi over 4. So now we need to get a formula. So magnetic field due to a wire, and this could be found doing Ampere's law, but it's usually acceptable to just memorize this one. Mu naught I over 2 pi r. So current, the more current you have, the stronger magnetic field. The further away, the less magnetic field you have. And mu naught is just going to be 4 pi times 10 to the negative 7th, just a constant. So I'm going to call this, that's wire 1. So let's see here. If we say wire 1, this will be the hard one. The magnetic field, the magnitude is going to be mu naught I over 2 pi r. And mu naught is going to be 4 pi times 10 to the negative 7. We're going to have current, which is 10, which is convenient, all over 2 pi, which is convenient because it'll cancel with part of the 4 pi up top. And then r is going to be the distance away. So we have 10 centimeters, look at this in terms of triangle, 10 centimeters here, 10 centimeters here. So that's going to be square root of 200, which will be square root of 2 times square root of 100. So 2 times the square root of 10. Yeah, I'm good with that. 2 times the square root of 10. So a little bit more than 2 centimeters. But I'm going to call it square root of 2 times 0.1 because that's 10 centimeters, which is 0.1 meters. Okay. Yes, I'm happy with that. I'm reasonably happy with that. So we'll do some canceling. This goes 2. That becomes 10 to the negative 6. And this is 10 to the negative 1. Which we put up here becomes 10 to the 1st, which then becomes 10 to the negative 5th. And so we have 2 over square root of 2 times 10 to the negative 5th. Okay. Yep, that's reasonable. So now, though, we want to look at this in terms of a triangle, because the magnetic field is going down to the bottom left at a 45-degree angle. So we're going to have this right here is going to be 2 over square root of 2 times 10 to the negative 5th. And so B1 in the x direction, yes, is going to be 2 over square root of 2 times 10 to the negative 5th times cosine of 45 degrees. The cosine of 45 degrees is going to be square root of 2 over 2. So 2 over square root of 2 times 10 to the negative 5th times square root of 2 over 2. Convenient. I'm glad I didn't simplify the square root of 2 over 2 earlier. And we have 10 to the negative 5th. And then we're going to do the same thing and find it for the sine of 45 degrees, which happens to be the same as the cosine of 45 degrees. So when I rewrite this, B1 is negative 10 to the negative 5th in the x direction minus 10 to the negative 5th in the y direction. And the negative x and negative y have to do with the fact that this vector right here is going to the left and down. Okay, so that was the hard part. Now we're going to find the magnetic field at due to wire number 2. Magnetic field due to wire number 2, same formula, 4 pi times 10 to the negative 7 times the current, which I think is 8. Yes, 8 amps, all over 2 pi times the radius, which is 0.1 meters, which I'm gonna write as 10 to the negative first. All right, do some canceling. Figured I need a calculator by now. Kind of proud that I haven't. So 10 to the negative first on the bottom is the same as 10 to the first up top. 10 to the negative 7 and 10 to the first become 10 to the negative 6. And we have 16 times 10 to the negative 6, which is the same as 1.6 times 10 to the negative 5th. I just want to have the same units for both of these. It makes sense, that's a little bit bigger. That's 1, is 1.6. And so I'm going to say that B2 equals 1.6 times 10 to the negative 5th in the x direction. All right, so we want to find the resultant magnetic field. And so I'm going to call this B net for net magnetic field. I guess we could call it BR for magnetic field resultant, but I don't want to. So we're going to do it this way. So we're going to have 1.6 minus 1 times 10 to the negative 5th in the x direction. So 1.6 plus negative 1 plus 1 times 10 to the negative 5th plus negative 1 times 10 to the negative 5th in the y direction. And so then we're going to have 0.6 times 10 to the negative 5th in the x direction minus 1 times 10 to the negative 5th in the y direction. Yep, and that's going to be our B net. And if we want to find the magnitude, we could just draw a triangle here. So it'd be to the right 0.6 and down 1. And we could find this angle, and we'd do 0.6 squared, 1 squared, square root together our magnitude, and we could find an angle. But personally, I like it this way better. So I'm going to leave it as thus. So long story short, to kind of recap what we did here, we had 2 wires. We used the right-hand rule. Place your thumb along the direction of the current, wrap your fingers, and the direction your fingers wrap is going to be the direction of the magnetic field in a circle around the wire. We then found the magnetic field for each of them. This is actually a 45-degree angle. Doesn't look like it, not drawn to scale. Then we found it at a distance of square root of 2 times 10 centimeters. Did all the math. Some things conveniently canceled. Did all the math on wire number 2. It was simple enough that I didn't really need to cancel. When their powers combined, actually they weren't really powered, when their powers were added, when I added the 2 magnetic fields, then we got the resultant magnetic field, which I left in X and Y notation. Hope that helped. See you next time.